I am going to talk about why model design still matters in an era where things are getting bigger. But let me take you back. Do I have the wrong? There we go. Back a couple hundred years. And I'm going to talk about two stories about the remarkable and unlikely way that humans follow their need to explain what's happening and come out with new knowledge. So here is Vasco da Gama, 15th century Portuguese sea captain. And in 1497, he sets off with 170 crew, 4 ships and an armada. And his goal is to find a way to get to India via sea around Africa. There are no engines at this era, so they have to go deep into the Atlantic Ocean to catch westerly winds. They go around the Cape of Good Hope, and 6 months later, they are in modern-day Mozambique. And I'm going to quote something from the ship's journal, which is all we have from this voyage, where it writes, "Many of our men fell ill here, their feet and hands swelling, and their gums growing over their teeth so that they could not eat." And this is, scurvy is taking place. This is very common at that era. And a couple of months later, they sail into Malindi. This is southeast Kenya today. And there are these local trading ships that trade with them. And amongst the items are these oranges. And it's noted here that they're even better than the ones in Portugal. And 5 days later, all the sick get well. And the journal at least attributes this to the good air of this place. But we know what's actually up. But there's a lot of confounders here. Then they sail over to India. They have some tailwinds behind them. They cross the Arabian Sea really quickly. They get there. 3 months later, they head back. There's monsoon season. The journey back is brutal. It takes 4 months. Half the people remaining die. They limp back to Malindi. And this time, there's a revealing passage in the journal where the sick specifically ask for oranges. So even though there were some confounders in the journal, originally was like, the air of this place is so good, the sick are like, no, give us some of those oranges. 250 years pass. There's a Scottish physician by the name of James Lind. This is a picture from his journal. And he does this remarkably prescient and early randomized trial. He gets 12 sailors that have scurvy. He splits them up into groups of 6, 2 each, and then gives them different treatments. And no surprise, he writes that the most and visible good effects were perceived from the use of the oranges and lemons. A lot of signal here. What does he deduce? He deduces that the causes of scurvy, which he devotes a lot of his text to, are from the moist sea air, which will certainly be rendered still more noxious in a confined space, and the lack of fresh vegetables and greens for the crew. So his advice to ships is just have lots of ventilation, give lots of fresh greens to your crew. And none of this works, right? And as for the oranges and lemons that do so well, he advocates boiling the juice so that it survives the journey. And we now know that just gets rid of the vitamin C. So 30 years later, Cook of Captain Cook fame, he tries the boiled lemon juice and finds it ineffective. So nobody tries this. Thankfully, about 50 years later, the Royal Navy realizes what's up, and actually they mandate daily lemon juice. But because nobody understands the cause here, 40 years later, when lemons become supply constrained, they're substituted by limes. They don't have as much vitamin C, and the cure is lost. Scurvy comes back. And it's not a long time after that people actually figure out the lemon juice was the reason. So the actual understanding of what's going on takes about 200 years from Lind's original randomized trial. First, someone has to do a synthetic diet experiment to figure out that there are some things called micronutrients, that macros aren't the only thing that matters. Then Holst and Froelich do this very lucky experiment where they induce scurvy in guinea pigs, which like us, can't produce their own vitamin C. So a nice lucky strike. And then vitamin C is isolated, and it's demonstrated that it has this anti-scurvy properties. Lind, 250 years ago, had no chance. There was no chance he could figure out. There's a whole bunch of prior knowledge required. Second story. It's 1576. I'm going to butcher some names here, but Tycho Brahe, Danish astronomer, he convinces his patron king to build him the largest naked eye observatory ever made. This thing up here, you can see him at the bottom left looking up. And actually, I was curious, you have a lot of scientists here. Has anyone looked up at the sky and tracked, let's say, Mars over multiple nights as it's moving across the sky? I did this by accident, but has anyone ever done this? Okay, maybe I'm just weird. You can do this, but not at the scale of Brahe. They did this for 20 years, tracked the 5 known planets at the time, and amassed this massive data set that was very, very accurate, 5 to 10x more accurate. And Brahe had an assistant, a Johannes Kepler. And after Brahe dies, Johannes gets this very jealously guarded data and makes this incredible fit to it, where he relates the orbital periods of these 5 planets to the semi-major axis of the elliptical orbit. He doesn't live to see this, but when Neptune and Uranus are discovered, it fits perfectly. How did he do it? Well, he had some very consequential priors. Unlike Brahe, who believed everything revolves around the Earth, he believed in Copernican heliocentricity, that things revolve around the sun. He studied music, so for him, the idea that the orbital period, and the distance are related is natural. He had some wrong priors that helped him. He believed that the Platonic solids circumscribed, the shells circumscribed the planet's orbits, which is wrong, but it led him to believe in simple mathematics. And then he also had this idea of protogravity. He thought there was a immaterial emanation from the sun that reduced over distance, it was very gravity-like, that pulled the planets along. Why? Because he needed a cause. He's very focused on little errors of prediction. He writes, if you fit a circular orbit to Mars, you will be off by 8 arc minutes on the actual measurement. And he writes, these 8 minutes alone will have led the way to the reformation of all astronomy. Okay, 150 years passes. Newton writes the Principia. The laws of gravitation are out there. Fellow comes along, another Johannes Bode, a German astronomer, and he says, no, that was all wrong. I actually have a different fit. The orbital duration doesn't matter. If you assign an index to each planet, there's this perfect line you can put through, and not only does it explain the current planets, there's a little gap, and there should be something there. That creates a search. Ceres is discovered right there. And then Uranus is discovered, and it fits perfectly. When I was researching this, I left very much in admiration of the confidence of this guy, right? Because like Newton has already come out with the laws of gravitation, and Kepler already has the right fit. But Bode, he fits the data. He's made correct predictions. It's simpler. Right? It has all the hallmarks of a good theory, but it's wrong. Bode's theory actually turns out to be Titius's theory 15 years earlier, and if you look at what their priors were compared to Kepler's, they were aesthetic and theological. He writes in this little footnote, he says, you might notice a very curious pattern if you do this thing where you assign indices and fit this curve, and he writes, should the Lord Architect have left the space empty? There's no need for a cause, there's an aesthetic to the world, and that space should be filled by something. So the reason I told you these 2 stories is because there's a pattern here where people take observations of the world, but crucially they combine it with these inductive priors, these things that they believe that induces the predictions that they make. And that creates new science and it recycles. Okay, what about AI? And like Margaret, I'm glad she did the categorization. I'm going to do something similar too, because AI is just not a useful term anymore. So let me describe 2 timelines, and I'm thinking about what happens to science, which is, one is we take the current LLMs, maybe Anthropic or Google, because let's be real, it's not going to be OpenAI. They create an AI scientist that just does the job, uses robots, does experiments, takes observations, and then that's it. And I'm not going to talk about that because, I mean, what's there to say except for what did Naroshli say, the monster minds among you, that you have climbed peaks already. Congratulations, because there's going to be no more of that, probably, if that happens. The other timeline is that humans there's still room for scientist humans, and we use tools and scientific AI models to really supercharge our ability to do science. And I'm going to focus on that. And there's really only one model here to talk about. And I was thinking about how to provide evidence for there being this paucity of the examples for this, but we've just heard so much about AlphaFold these 2 days already that I think it speaks for itself. There's just not that many examples of models that use, let's say, deep learning or more modern AI techniques that have been really consequential for science. And I'm going to zoom in on AlphaFold and talk about where are all the little bits of inductive prior that the architects of this model have put into it. So we saw a little bit of this in Sean's talk, and it was really cool to hear about Hammer and how it provides the MSA here. But I want to talk about what this means for AlphaFold, which is the people who designed it, they knew that nature uses these Lego blocks and composes them, and that these homologs that are nearby are really important for structure prediction. So rather than the model just looking at the target input, it is forced to look at the homologs that Hammer introduces. This is a very strong prior. It's not at all obvious. You need a lot of prior knowledge to know this. The other one is that because we know how maybe some of the physics works, we know that the relationships between the residuals are important. And the model is forced to represent that. That's another inductive prior. On the output side, AlphaFold 2 at least, which is the one I'm talking about, it doesn't just output the locations of all of the atoms. It actually outputs them in a relative frame. So it means if you have a really long chain and you're way over here, you don't really have to worry about what's happening up here. You just zoom in on this little location. And there's many more. There's many more that are not even in the deep learning model. After the output comes out, you put it through Amber, you do post prediction energy minimization so that some of the messed up physics gets resolved. If atoms are clashing, you pull them apart. I want to make an analogy for all this to the priors we looked at before, how Kepler and Lind and Holst and Froelich were looking at those observations through those priors. There's an analog here in the way AlphaFold is using this information. And why does it have to do that? Here I've got a key ratio in machine learning models, which is a ratio of the amount of data you're training your model with to the number of parameters it has. And highlighted in red is a reference value from a paper, a notable paper, Chinchilla paper, where they found that for language models, it was optimal to train at a 20-to-1 ratio. 20 data points for each parameter. And you can see some language models there. Look at AlphaFold. It's on the far left. It's a 0.38. AlphaFold is about 100 million parameters. It was trained on the PDB. The PDB took billions of dollars to produce with X-ray crystallography, cryo-EM, whatever. But there was very little data compared to a language model. So that's one reason AlphaFold needed to have all of these inductive priors, because it had to be super efficient. It couldn't figure out those inductive priors itself from the data. But there's a second reason, maybe more interesting, which is AlphaFold, kind of like what Kepler was doing, was trained on raw observations. Just the sequence, and the output was the locations of the data. Compare that to when you train on text. Let's say if I read a book on the motion of the planets, and it says something like, I don't know what, it basically describes it to me that the planets revolve around the sun, yada, yada, yada. That text is basically piggybacking on all of the work that Newton, Kepler, and so on have done, and that it has that structure. And you might say, okay, that's like some fancy textbook. What if it's just a Reddit thread about cheese? I will then say that, okay, the people that are talking in Reddit about cheese, they're saying what you can do with cheese, what it tastes like, what it looks like, what it feels like on your tongue, how it works with other food items. That's not information that's available if you like molecularly look at cheese. So text has this different quality to the raw observations, and this is why AlphaFold needs all of these priors, because it's not able to piggyback on all that human understanding. So okay, we have this problem. We have these small data sets. I used the term yesterday. This oil that AlphaFold was trained on. We don't have it for these other fields. So is the solution to just drill for more oil, so to speak? Is that what we should do? And I think this question maybe it fits the current zeitgeist because things are getting bigger. We've just heard Margaret was talking about LLMs. I mean, over the past 4 years, we have seen what I would think of as the birth of a new kind of intelligence that just wasn't imaginable 4 years ago, and now it's in your pocket. And these language models, the general architectures, all based around the transformer architecture, they're trained on enormous amounts of data. And to put this into perspective, DeepSeek, which is the latest model out of China, which is, let's say, 6 months behind, this is controversial, 6 months behind the US, is trained on 32 trillion tokens. If you read a book, 400 pages, every day, it would take you 580,000 years to read 32 trillion tokens. So there's a lot of information being put there, so we have to ask this question of, like, should we just scale up the data? And if we do that, can we just get rid of all those priors? Because the AlphaFold priors are difficult to implement. They require expertise. They require someone to, like, know how it all works and put them in and try them. To give, like, a demonstration of this, I'm going to show you what happens if you train some of these models on problems that are hard to cheat on. They penalize or hostile to memorization, which is, one of the things that generalized models can do. They can memorize. So here we have 3 bodies in gravitational motion, right? So we're sort of giving a nod to Kepler and what he was doing. And depending on the initial conditions, you can have very regular motion on the left, or you can have very chaotic motion. But the underlying physics is super simple. So we want to train a model to predict this system, and hopefully, in doing so, it figures out how the dynamics works. So what I'm going to show you is a group of 5 different architectures, starting from almost no prior in the transformer. This is the model behind all the LLMs and the multi-layer perceptron, down to models which have a physics prior. So these are models where you kind of slap them on the hand if they produce outputs that violate physics. And to a model that just encodes the prior that you should think about this problem in pairs. Because we know each body attracts another body, so this pairwise relationship is important. And the data we're going to train this on, we have a simulator, so we have kind of infinite data, is these rollouts of the 3 bodies moving, and we're going to give the positions and velocities and the masses to the models, 100,000 trajectories. And the only thing I did is I filtered based on linearity, so that in a constant time delta, there's not crazy motion. Like if the bodies get really close together, they'll slingshot, there'll be a lot of nonlinearity. So that's been filtered out. So the models have a nice linear regime to hopefully learn the gravitational laws and predict. Here's what this looks like when you train these to the point of plateauing. You see the log scale on the left, so the error isn't moving much. And what's really interesting is that the transformer does the worst, and I'll talk about, but the transformer is the most general. And then the models do better and better with some of the priors that they had. The ones bunched up together are like the physics prior, the Hamiltonian prior. And then there's a graph neural network that's about 10x better than the others, with the same data. And this is what it looks like if you, not just with the little training validation, what it looks like if you actually roll this forward. The graph neural network is just doing so much better than anything else. The transformer is close. But let me show you what this actually looks like. So these are the predictions. This is the transformer doing a prediction. The solid line is the ground truth. That's what's real. That's what the integrator says. And then the transformer is the dashed lines. These models are all about 36,000 parameters. And so these are small models. But the actual dynamics, they have a very low Kolmogorov complexity. So theoretically, the model should be able to learn this. Look at what the transformer is doing. It's kind of, I don't know, I would use the term memorize. It's memorize these rotational orbits, but applied them completely incorrectly. Not as relations between bodies. And I'm showing you the graph neural network. It's remarkable. While there's some error, it's clear that the relation between the bodies is preserved. And of course, because the model's architecture has a prior for this, it can't not do this. So it doesn't have to learn this from data. Okay, so maybe no surprise, models with these inductive priors are much more data efficient. We saw the curve for the graph neural network dip so much lower. And think about the PDB. There's only so much of it available, right? So you want to really maximize how much you take away from it. But that wasn't the original question. The original question I asked was, can we use general purpose models like the transformer and scale those up? Because then we don't need inductive priors, we don't need expertise, we don't need to be designing these models. So let's do that experiment and train bigger models on more data, because we have infinite data in this 3-body mass problem. So here, let's double the model size with the same number of parameters. The hypothesis here is that the models just don't have the capacity to learn this, although that would be an interesting theoretical result because they should have the capacity given the Kolmogorov complexity of what it is. Minimal improvement. But let's just go all out. Let's take a 1,000,000 parameter transformer and train it with 3 times the data. So there should be no data limitations, nothing like that. And the loss is actually not as low. The error is not as low as the graph neural network, but it ends up doing better predictions on the trajectories. And I won't go into the details of that, but it's like a little interesting quirk here of the way these errors are measured. But it basically does better on the in-distribution trajectories, meaning trajectories that look like the ones that we trained it with. It does much better than the much smaller graph neural network. And so I have a follow-on question. So it's doing better, okay? It's predicting better than the graph neural network. Has it done that by figuring out the underlying dynamics? Has it done that by deconstructing nature and figuring out there's this pairwise relationship between the bodies? Newton was right, it's the gravitational laws, I'm gonna just run that forward. And I'm just gonna go back a little bit. The reason I'm asking that is because we care about that for 2 reasons. One is we want to know that it predicts correctly out of distribution, because the stuff that's in distribution we already know. The second one is we want to inspect it to figure out how it's doing it. I'm going to take you back to AlphaFold. We don't really know how AlphaFold works, how it makes those predictions, but it sure would be interesting to know how it works. And so these are 2 reasons why we want it to have backed out the dynamics. It was not hard to figure out that the answer is no. Here's one prediction where you see again the dashed line is a transformer doing really well on the 2 orbiting bodies, but there's that 3rd body in the background, I don't know if you saw it, it's doing well and then it just veers off track for no reason, completely non-physical. Who knows what happened? Maybe the transformer had really dialed its approximation into this little local area. These are all normalized trajectories, so the numbers don't get very large, but something strange is happening. That was in distribution, the initial conditions, but let's go out of distribution. This is closer to what Kepler was working with. We have a sun, earth, moon system. The moon is the little green thing, but we can't see it, but it's all in a plane. If you think about our solar system, the planets don't just fly off the plane. There are no forces to make them do that. So the prediction should never be outside of the plane if what is creating the prediction is something akin to the real dynamics. Look at what the transformer is predicting. It's just completely, it's pulled the sun out of its plane, flung it out. So, okay, we're out of distribution. But I only know this because I know what the real answer is. Right? These are only useful if I don't know what the real answer is and I'm getting a prediction. Okay, so hopefully there's some interesting ideas there. I'm going to try to bring it all together, answering the question why model design matters. I have 3 answers, maybe in progressive order of controversy. Okay, so the first answer is, at the frontier, where I think all of you enjoy living, the data is just very scarce. There's not a lot of oil to be found. And so whatever you do has to be extremely data efficient. Like Kepler did that incredible fit with 5 data points, 5. Holst and Froelich, when they did their induced scurvy experiments with guinea pigs, they had less than 100 samples. Right? It's just really hard to get large amounts of data. So that's one reason you want inductive priors. That's one reason why AlphaFold looks the way it does. The second reason is that if you train models on observational data and not text, you don't get to piggyback on all the people that figured it out and wrote it down. You're just dealing with numbers and colors, and that's it. And so this is not a new idea. If you go back 1920s, Saul Wright did this experiment where the end result was path analysis, SEM, there's different names, but basically there's an induced structure that you sit on top of when you do your analysis to make sure that whatever you come up with has some semblance of causality. And we care about that because we want these models to mirror the causality that happens, in the real world. And the third, and I'll go back to Kepler here. Imagine Kepler had trained, in the 1600s, a kind of mechanical box that when you fed it the inputs of the planet's motion, it would just predict perfectly the future observations, right? Like that line there, that's Tycho Brahe's observations. It just perfectly predicted them. I don't think, maybe be challenged on that, I don't think we would at that point say we understand the dynamics of the solar system. We would not. We would just have a perfect predictor, and that's really useful. It's super useful. I mean, we've heard how useful AlphaFold is. But it's just a precursor to understanding what's actually happening. And we now have the ability to inspect these models. You can put probes in, you can do all kinds of things with them to figure out how are they doing this. And so it's really good to have models that have inductive priors because it tells us already how they might be doing certain things. I've heard that in this era of scale, of bigger and bigger, billions of dollars spent on compute, it can be a little bit discouraging because it feels like advances in AI are reserved only for those which have access to these resources. But I think that maybe the takeaway, the thing you will take away from this is that there's actually a lot of greenfield opportunity to create smaller models that don't take a lot of resources to train, but have inductive priors based on the expertise of the people that know these problems really well. And I hope that because of that, there's just going to be more AlphaFolds in the year ahead, so we don't just have this one example. Thanks.
That's great. So I'll begin with a question. So staying with AlphaFold, my understanding is that one of the huge inductive priors, as you would call it, is understanding the probability of proximity of two amino acids to each other in a protein. So it's not just raw sequence information that you list in a linear sequence. It's actually having an incredibly useful spatial constraint that reduces the size of the problem. Would you make a comment? And so this, of course, ties to multiple sequence alignment problem that Sean mentioned yesterday. Would you comment on this, please?
Yeah, I didn't go through all of them, but there's a bunch of priors in AlphaFold that imbue it with this knowledge. For example, on the input side, AlphaFold does look up a structure database, which has examples of these structures and how the residuals are located on it. When it does updates to its representations, there's a part of the architecture that preserves the triangle inequality that you'll have if you have, let's say, three residuals, and you update on them, you have this triangle inequality that's preserved. So there's a lot of, I would say, physics, stereochemistry knowledge that is in there so that it can extract the most from that really relatively small data set that it's using.
Now it's on. Hello? Okay. So I have a question that's probably relatively basic, but I keep seeing it used everywhere and really don't have an understanding of like what exactly is a token. And then from that, when you're using any of the big LLM models like DeepSeek or Anthropic, and it says that like you're using a token, what does that mean? And how does that like impact the usability of the LLM?
You can think of as a token as the LLM's alphabet. It just doesn't end up using our alphabet. It uses an alphabet that has a really advantageous statistical probability. For example, if a word occurs very frequently, like like words of very high frequency, that'll be a token. There'll be a token reserved for that word. But if a word is not very common, there won't be a token just for it. It'll actually be made of a couple of tokens, each representing like a little bit of it. And that splitting that up is something that's done statistically by analysis. So I think that the mental model for me is that it just uses a different alphabet that ends up minimizing the number of it's less number of tokens that if we're using, let's say, just our alphabet, A, B, C, D, and that's just helpful in training them.
Questions for Nima?
I ran out of time in my talk to make this point, since I showed at the very end one AlphaFold slide. Do we have a comparable database that can train AI to dramatically accelerate attacking undruggable proteins with chemicals? In other words, where is the comparable database to the 240,000 proteins in the PDB? And what is your vision for how that problem is going to be addressed?
I'll just caveat by saying I don't really know enough about the domain, but from a machine learning perspective, I think there are these happy accidents where the PDB was just there by the time that the deep learning architecture for AlphaFold was discovered. I don't know if that's repeatable. So I think part of my call to action for these smaller models is that at the edges, likely we're going to be dealing with like ones and twos. Extremely limited data sets, unless someone finds a way to like do massive collection, which folks are doing right now, like in cell perturbation. There's large data sets being produced, but I think it has to be created.
No, I was going to make the point though that the PDB consists of something like 200,000 structures. Maybe it's not that many. Hold on, I'm trying to get the numbers right. I was going to say that the database isn't very big, but there's 30,000 folds. So you've got the ability to be able to predict another structure based on that. The induction from that data set isn't particularly large. Would you like to comment on that fact? Because it might answer the question that's just been asked, which is where is another data set that's like the data set that was available for DeepMind to do what it did?
Yeah. Okay. This is really interesting. So I mentioned that nature composes these building blocks, like you mentioned. There's only so many folds. The inductive prior in AlphaFold that makes it pay attention to that is the MSA. And actually the structure module, the structure template library, both are like find the building blocks in this during training, but during inference, look at those homologs and nearby structures in the structure library and reuse those. I think you were hinting at maybe a database that's there. I unfortunately don't know enough about the kind of structure prediction side of it, but I'll just use this abstraction that answering that question and imbuing a model with an inductive prior to use it is exactly what I'm advocating for, to be able to get the most out of what is a limited set of observations.
Hi, I enjoyed your talk. I guess my question is about which components of AlphaFold do you think made the biggest difference in the kind of the breakthrough ability of it to do the accurate prediction? Because it seems to still have a lot of components that are looking at the biophysics and making sure that the energy functions work and doing all of these filtering and pre-processing and everything. So if you compare it to something like a model that was, state of the art before, something like Rosetta perhaps, or something like that, which components really made the leap?
Short answer is I don't know. I'm trying to figure out if there was an ablation study done in the actual AlphaFold paper, whether you sort of remove things and see which one has the most effect. But I think maybe an illuminating next step of the story is AlphaFold 3. AlphaFold 3, it was in that slide that I had, it was trained on a 20x ratio. The same as our kind of gold reference in the chinchilla paper, 20x. But it all came from AlphaFold 2 predictions. So the data was actually synthetic. And if you look at the architecture of AlphaFold 3 versus AlphaFold 2, and I want to make sure I'm like precise about this, the only inductive prior that's removed is on the output side. So AlphaFold 3 directly predicts the locations of the atoms using a diffusion model rather than outputting in the local frame with the invariant point attention, which was the real output side inductive prior. So that module was discarded, replaced with a diffusion module, but then what took it to get there is just gobs and gobs of AlphaFold 2 predictions. So it was bootstrapped off of that. I feel like I didn't answer your question because I don't actually know, but you'd have to do like an intensive ablation to just pick them apart and see.
So my understanding of the question that you asked is that it was exactly the decision to focus on probability of proximity of two amino acids to each other in a polypeptide chain. What it does for you, it creates significant constraints to how a protein could fold, where you can then let the molecular dynamics take care of it, avoid clashes and all of that. But reducing massively the size of that computational problem with point context, or really the likelihood of them, is what led them to be so successful.
So in some sense, you were helping compress the search space to make it more computationally
That's exactly
tractable?
right. And I think what's exciting about the presentation that Nima gave us is, the challenge when you have this massively complex problem is to find such ways of simplifying things.
Yeah, one thing I'll add to that is, if you think about going from a sequence to 3D structure, that's a difficult problem. But compare it with, for example, going from a perturbation to some change you observe in the cell. And one is modulated by physics and folding. The other one is modulated by like the operating system of the entire cell. Yes. The latent space is massive. So if you just trained end to end, the data requirements are really large, and then what I was trying to show is that it's not guaranteed that a general purpose model will actually back out the kind of mechanistic system that's giving the answer. So if you could help it along by putting an inductive prior based on what we know, and it's difficult, but if you could do that, as you said, you would reduce the search space because the model doesn't have to figure that out from scratch.
Okay, let's thank Nima one more time.